Marhaba. Okay, in this session we want to talk about logic. Logic as a word, it's a Greek word and it means the word, al-kalima. It also means thought or reason. Okay. These are the meanings of the word logic in Greek. And now we use logic as a system composed of two parts. So here is logic, our system. We will build it together in this whole chapter of logic. So the first part of logic is a precise language. So we want to learn the language of logic. So this is a precise language, and using this language we will express our thoughts and statements in mathematics. And the second part of logic is a collection of deduction rules. Okay, so this is a language which we will introduce its alphabet if you want, and then we will introduce rules to compose sentences from the alphabets and so on, similar to our natural languages of Arabic and English. Okay, and then we use deduction rules we start with statements, we write them, and then we use the rules to deduce more and more statements, and we use the rules to check the validity of our conclusions, like whether the conclusions we deduce are true or not. Okay, now one type of logic, which is the topic of this session, is propositional logic. Propositional logic. Now, propositional logic was developed first by the Greek philosopher Aristotle, and this was done like around more than 2,300 years ago, which means like 300 years BC. Okay, now the building block of propositional logic, it's called a proposition. So let me define what do we mean by a proposition, and this is the important definition of this session. So a proposition is a declarative statement. Okay, sorry, is a declarative statement which is true or false, but not both. Okay. So again, look, what is a proposition? This is important to understand. A proposition, it's a statement, but not any statement. It's a declarative statement. It's a statement which declares an opinion. And this statement should be either true or false, but not both. So this proposition, we say it should hold a truth value. We should decide whether it's true or false, and it can't be both. Okay, so if you are given a statement, to decide whether it's a proposition or not, you need to see if it declares an opinion, and second, to see if it's true or false, but not both. Okay, let's have some examples. So here is, look at this statement which says Cairo is the capital of Egypt. Okay, what do you think? Is this a proposition or not? First, we need to check, okay, it's a statement. Does it declare any opinion? Yes, it declares that Cairo is the capital of Egypt. So the first condition is satisfied. The second condition, it is true, because in this world, Cairo is the capital of Egypt. So this is a proposition and it's a true. So we say this is a true proposition. Okay, let's have a second example. say Sydney is the capital of Australia. Okay, is this a proposition? Yes, because it's a statement which declares an opinion. It declares that Sydney is the capital of Australia, so it's a declarative statement, but it's a false proposition because the capital of Australia is not Sydney, it's Canberra. Okay, so this is a false proposition. It's a proposition, but it's a false one. Okay. Now let's have another example. Okay, what do you think of this? 4 times 487 is equal to 1948. Is this a proposition? Well, first, yes, because it declares an opinion. You see, we should be able to read mathematical symbols as English sentences. So what is this statement? It says that the product of 4 and 487 is equal to 1948. Okay, so this is a statement. It declares that if you multiply these two numbers, you get this third number, 1948. And if you check it, you'll get a true answer. So this is, yes, it's a true proposition. Okay, it's a true proposition. It both declares an opinion and it has a truth value. It's a true proposition. Okay, let's have another example. So what about this sentence? What time is it? Okay, what do you think? This is not a proposition because it doesn't declare anything. It asks for something. So this is not a proposition. There's no opinion declared here. Remember, a proposition is a declarative statement, okay? Not a proposition. Now let's see another example. Okay, x plus 2 is equal to 5. Well, this is a declarative statement. It declares that if you add 2 to x, you get 5. It declares an opinion. Now, is it true or false? Well, it depends. If x is 3, then yes, it is a true proposition. It's a true statement. If x is 0, then 0 plus 2 is 2, which is not 5, so it's false. So here, its truth value depends on the value of x. So this is a declarative statement which is neither true nor false. We can decide its truth value. And so it's not a proposition because a proposition must be either true or false, but not both. So here again, it's not a proposition, but for a different reason. So it's a declarative statement, but it doesn't have a truth value, not a proposition. Okay. Now, we will look at the propositions here. So you see propositions are statements. So here it's Cairo is the capital of Egypt. Sydney is the capital of Australia. 4 times 487 is 1948. These are declarative statements. These are propositions. And now instead of writing sentences, long sentences, we will represent them by letters. So for example, we can represent Cairo is the capital of Egypt by the letter P. Sydney is the capital of Australia by the letter Q, and 4 times 487 is equal to 1948 by the letter R. Okay, so we will use these letters P in general, P, Q, R, S, T. We can also say P1, P2. We can use all of these letters to represent, so these letters will represent in this course propositions. Okay, so when you see such a letter, you think of S. Maybe S says Cairo is the capital of Egypt. So S is a declarative statement which is either true or false, but not both. Okay, and we call these letters, we call them propositional variables. Okay, propositional variables. So these are the simplest propositions. the variables. And now what we want to do, so you can think of this as the alphabet of our language. Remember, logic, the first part of logic, it's a precise language. This is our building blocks, the propositions. And now using these propositions, we want to build more and more complicated statements. How are we going to build them? There are precise rules to build these. Okay, these are different than the deduction rules. I want to tell you rules how to build statements. We are still in the language part. Okay, so these methods of building statements were first developed by the English mathematician George Boole. George Boole in the 1800s in his book Laws of Thought. Laws of Thought. An impressive title. So he wanted to put laws to do thinking. Okay, so what are these methods that will enable us to build more complicated statements? So we start, what is the starting point? This is the start. We start with propositional variables, P, Q. Let's say we just need two letters for now, P and Q, and these are letters which represent statements, declarative statements. They represent propositions. Now the first method to build a new statement is called negation. So what is the negation? So the negation of a sentence, of a proposition, so the negation of P, of a propositional variable P, is not P. Okay, so this is the new statement, not P, which says, what does it say? It is not the case that P. Okay, so we represent all of this. It is not the case that P by this symbol, not P. Okay, this symbol is read as not P. Okay, now see what we are doing here. We start with a statement P and we introduce a new statement which we call it not P. Okay, now, and what we want to start with a proposition and get a new proposition. So the new proposition, what again, not P, should be a declarative statement which is either true or false. So what is the value of not P? Well, it depends on P. And now we represent the truth value of not P using a table which we call the truth table of the negation. So here we have P and here we have not P. Okay. When P is true, so P, again, P is a proposition. It's either true or false. If P is true, then we define the truth value of not P to be false. And when P is false, we declare the truth value of the negation to be true. Okay, so we are building our language, we are building the logic we want to use in this way. Okay. So start with any proposition, P. We construct a new proposition, we call it not P, and we define its truth values as follows. Not P is false when P is true, and not P is true when P is false. Okay, let's take an example. So suppose P says, it says, Karim can swim. Okay, so this is a proposition, it's a statement, it declares an opinion that Karim can swim, and we represent this statement by P. Now let's see what is our new statement, the negation of P. It's denoted by not P, and what does it say? It is not the case that Karim can swim, or if you want, Karim cannot swim. Okay, now suppose really that Karim can swim. So P is a true statement. In this case, not P will have the truth value false. Okay, we use T for true and F for false. Okay, so see that the truth value of not P depends on the truth value of P. So because P is true in our example, then not P is false by definition. This is how we defined the negation. Okay, now the second method to construct a new statement is using conjunction. Okay, conjunction. Okay, so what is conjunction? Suppose we have P and Q. Okay, now we say the conjunction of P and Q is the statement written as P and Q. Okay, so this is a new statement which we build using previous statements P and Q. So sorry, these are propositions, and we create a new proposition denoted by P and Q. And how do we we need still to make P and Q a proposition, we need to give it a truth value. So the truth value of P and Q depends on the truth values of P and Q. We define P and Q to be true only in one case, when both P and Q are true. Okay, so let's do the truth table. We have P here, Q here, and this is the new statement P and Q. Now here we have four scenarios. P could be true and Q true, P true and Q false, P false and Q true, and P false and Q false. Again, we define the truth value of P and Q to be true only in the first row, only in this scenario, when both are true. However, when one of them is false, or both are false, we declare P and Q to have a truth value false. Okay, so this is the conjunction of two propositions. Again, what we are doing here, we are starting with a proposition, another proposition, we create a new proposition called P and Q, and this is how we define its truth value. Remember, by definition, a proposition is a statement which is either true or false. So we must tell in the definition what is the truth value of the conjunction. Okay. Now, the next method is called the disjunction. Okay, so let me say what is it. The disjunction of P and Q, the disjunction of P of proposition P and proposition Q is the proposition P and then or Q. Okay, we read this as P or Q. Okay, where the truth value of P or Q is defined as follows, where P or Q is false only in one case, when both are false. Okay, so here we have P, here we have Q, and here we have P or Q. So notice that this symbol is, you can remember it by looking at the letter R in OR. Okay, so OR. And similarly here, the symbol for AND or conjunction, you can remember it by the letter N in AND. Okay. Now, how will we what truth value we will assign to P or Q? Well, let's see. We also here have four scenarios. Okay. Now, we said this disjunction will be false only in one case, when both are false. And in the rest, when P is true or Q is true or both are true, then P, this new statement, P, the new proposition P or Q is true. Okay, so this is the disjunction of two propositions. And let's have another method. It's called the exclusive OR. So the exclusive OR of P and Q. So again, P is a proposition, Q is a proposition. We now define a new proposition denoted by P and then circle inside it a plus, and we say P exclusive or Q. Okay, so this is a proposition. We write it in this way, and now we need to define its truth value. Okay, where the truth value of P exclusive or Q is defined to be true exactly when either P is true and Q is false, or Q is true and P is false. So when exactly one of P or Q is true. Okay, so we have P here, Q here, and now P exclusive or Q. Okay, so think now here again we have 4 scenarios. Okay, now we said only in these 2 rows P exclusive or Q will be true when exactly one is true. Otherwise, when both are true, then this new statement will be declared false, and when both are false, it will also be declared false. Okay, so to sum up, again, we have 2 statements, 2 propositions. P, let's say P, think of any proposition, so you can say outside is hot. Okay, so suppose outside is hot, it's a proposition. It declares that outside it's hot, and it could be either true or false. Say it is true, and Q could be another proposition, another statement which says flowers are red. Okay. Now we have P and Q, then using P and Q, so I think we start with these 2 propositions, and now we create a new propositions. We can create not P, we can create P and Q, we can create we can create P or Q, and we can create P exclusive or Q. So for example, not P, what is not P? It says that outside is not hot. And P and Q says that outside is hot and the flowers are red. P or Q says outside is hot and the flowers are red. Okay, so suppose for example, outside is hot, it's a true statement, and flowers are red is false. So saying flowers are not red. Now not P will have the truth value of false. Why? Because not P should have the opposite value of P. P is true, not P is false. P and Q is true only when both are true, but since one is true and the other is false, P and Q is false. P or Q is true because it is at least one of them is true, and P is true, outside is hot. And P exclusive or Q is also true because exactly one of them is true. Okay. And this is the end of this session.